Up to this point, we've been dwelling on the responses of systems to standard inputs, such as the impulse, the step, the ramp, and the parabola. And we've seen that each one of those responses provides us with a different way of looking at a system, with a different insight into its dynamics. But there's another standard input we haven't studied yet, one which is probably as important as all the others together. As you see, I'm referring to the sinusoidal input. Do you remember that we saw that the impulse response, that is, the response g of t, when the input of a system is a unit impulse, do you remember that we saw that it conveys all the dynamic information of a system, that it completely characterizes it? It does so because if certain input is applied to the system, let's call it u of t, so here we have u of t, we can calculate the output y of t as the convolution between the impulse response and the input itself, u of t. And in the Laplace transform, the expression of this fact was simply that if this is the Laplace transform of the input, the Laplace transform of the output was the transfer function defining the system g of s multiplied by the Laplace transform of the input. So g of t is a perfect characterization of the dynamics, and here then we would find, I don't know, maybe this response. Well, with the sinusoidal function, something very similar happens. And to illustrate that, let me assume that our input u of t is now a periodic signal. So let me draw it. So this is now the input to the system, and the fact that it is periodic means that I can apply a Fourier series and decompose it into an infinite sum of different sinusoids. So for example, u of t would be the sum of, I don't know, maybe this first sinusoid, this would be called u1 of t, plus this second sinusoid, u2 of t, plus a third one with higher frequency. So we would have to continue to add in infinite terms here, and all of them together would be our input u of t. Now, since our system is linear, that means that we can get the output of the system when the input is only u1, so let's call it y1 of t, and the output for the second input, y2 of t, and the outputs to all the rest of sinusoids. And as I was saying, since the system is linear, the sum of all those contributions would be y of t, that is the output of the system when the input is u of t. So in order to get to each one of these components, we have to find the response of the system to a sinusoidal input. So we can use Laplace for that. Y of s is the transfer function of the system times the Laplace transform of the input, u of s. But since let's say that u of t is a simple sinusoid, a times the sine of omega t. So a is the amplitude and omega is its frequency. That means that here, well, that means that u of s is equal to a omega over s squared plus omega squared. So if we apply partial partial fraction decomposition to this multiplication, we get all these terms, r1 over s plus p1 plus r2 over s plus p2, all those corresponding to the n poles of g of s, plus two terms corresponding to this input, which is s plus j omega, and its residue is called, I don't know, rs, plus the complex conjugate of rs over s minus j omega. Now, those of you who have seen the rest of the course may be objecting. This is not the response to a sinusoid in the way you defined them before. And you would be right. This is the response of the system to a function with this shape. This one, a function which is 0 up to the origin of time, because that was one of the requirements we saw when we studied the Laplace transform. So this is actually the response to a times the sine of omega t times the Heaviside step function. But we want the response of the system to a signal which goes back to minus infinity. And the way to do that, the way in which we do that, is we let enough time pass. We let enough number of oscillations to appear, and that way the output we get once all that time has passed will be equal, or will resemble the output when we have a sinusoid which comes from minus infinity. But if you think about it, actually that means that all these terms, if we inverse transform them, so we apply the inverse Laplace transform to each one of them, will tend to 0, because all of them, once they are transformed, are either exponentials, or real exponentials, or complex exponentials, damped oscillations. So when t tends to infinity, all of them disappear, and the only remaining terms are these two. Well, it is not hard to prove that these two terms actually define, if we again inverse transform them, define another oscillation with a different amplitude b, but the same frequency omega t, but with certain phase shift phi. And it is not hard to prove too that b is equal to a, the amplitude of the original input, times the absolute value of the transfer function of the system when s is made equal to j omega, and omega is the frequency of oscillation. Similarly, phi, the phase shift, is given by the angle of j omega. Why the angle? Well, if you think about it, g of j omega is just a complex number. You take the transfer function, you make s equal to j omega, being omega the particular frequency you are studying, and the result is just a point in the complex plane. Well, its magnitude, its distance to the origin, is this absolute value, and it defines the change in amplitude. And this angle here, or in other words, the arc tangent of the imaginary part of the complex number over the real part of the complex number, so this angle here, so this angle is the phase shift. And this is very interesting because it matches our day-to-day experience. If you think of a system, of a linear system, but one whose transfer function is not known, you can always perform an experiment on it. You can apply to it a sinusoid with amplitude A and frequency omega. So let me draw such input signal. This would be our input in the experiment. Well, the output of the system at the beginning maybe, I don't know, may have any shape, but if we let enough time pass, you end up with another sinusoid with different amplitude but the same frequency, and also with somehow delayed a little bit. Well, a little bit or a lot. There's some distance here, L, and this L is expressed in terms of radians by using cross multiplication. L is proportional to the phase shift, as the period, which is 2 pi over omega, is proportional to 2 pi. So the phase shift or the delay is just omega L. But the thing is, in our experiment we find that there's some change in the amplitudes. We measure the amplitude of the output, and that is B. And since the amplitude of the input was A, we say that B over A is the gain. We call this the gain of the system at that frequency. Well, it turns out that when we have the mathematical description of this system, we can get to that gain also by as we saw before, by calculating G of J omega. And the same is true for the phase shift. We measure this phase shift, but also we can arrive to that result by using the angle of J omega. So as you see, by applying sinusoids, by performing experiments on the system, we can get to the frequency description and eventually to the transfer function of a system. But my point here is that, okay, we can do this for one particular sinusoid. If we can do the same for all these sinusoids, obviously we have the overall output, because those gains and phase shifts are defining y1 and y2 and all the other y's, all the other components of the overall output. So a good way to represent that is drawing the frequency content of our signal. Maybe in our example we had a set of components such as this one, and then we can calculate the gain and the phase shift for all of them, and that way find the final y of t. Now, if what we have is not a periodic signal such as this one, if what we have is for example this input, which is aperiodic, still it has some frequency distribution, but it is not a set of infinite discrete terms, but a sort of continuous distribution of components, and the sum of all those contributions give the input u of t, and this is called, you may probably know, the Fourier transform u of j omega. And my point is that if we have the gain and the phase shift for each one of these infinite components, we can get the output as well. And actually the mathematical expression for that is that the Fourier transform of the output is just the transfer function of the system, but now with j omega instead of s, times the Fourier transform of the input. But the key is to have this, to have that complex number defining what happens to the sinusoids for each frequency of this distribution. That way, having the steady state behavior of the system for all those sinusoids of any frequency, we have a complete characterization of the system. We can always break down the input, calculate all the outputs, and then put them back together to find the output y of t. And it's interesting because we're doing that even though we're only working with steady state information. We're working with steady state information on what sinusoids concerns. But when we put back together all that information, we get characterization of the response both in the transient response and in the steady state, and also for any kind of input. So in the next video we'll learn how to represent graphically the information given to us by the frequency response.